Cool. Okay. I think now we can get started. Okay. Yeah. So today we have Andrew Eberhardt coming to talk. So he did his PhD at Stanford, where he worked with Tom Abel. And now he's at IPMU in Tokyo. Today he's going to talk about some simulations he's been running of fuzzy dark matter.
Okay. Thanks, Sark. And thanks to University of Minnesota for hosting me. So yeah, like Sark said, I'm going to be talking about some recent simulation work that we've done on looking at the implications of the classical field approximation for ultralight dark matter simulations. We've kind of done a lot of work on this throughout my PhD. This most recent work is probably going to be what's most relevant to what I'm talking about today, though. So for those of you who don't work on this model, I'll give a brief introduction to ultralight dark matter. So of course, everyone here probably knows that dark matter is kind of 5/6 of all the matter in the universe. When we talk about ultralight dark matter, we're talking about dark matter here at the very lightest end of this kind of 100 orders of magnitude, where we typically look for dark matter. And specifically, in the context of large-scale structure formation, we're usually interested in dark matter at 10 to the negative 19 eV or below. And then at these scales, you kind of get wave-like phenomena on astrophysical scales, so on about the order of like a kiloparsec. And this has a bunch of interesting phenomenology associated with it, like interference patterns between streams that are at the same position in phase space, rather than this kind of smooth density you would get from classical, like corpuscular particles. You get some sort of interference pattern in the density where the wavelength of the interference goes as the de Broglie wavelength associated with the difference in the velocity of the streams. And this gives you these kind of interference patterns on large scales that you can see here in this simulation of wave dark matter compared to the corpuscular counterparts. So in addition, the misalignment mechanism is probably the most popular production mechanism.
So it works for this as well.
Yeah. In addition to interference patterns, you also get things like quantum pressure versus purely classical. Like you don't need to invoke quantum mechanics to get this, but basically it's a term that resists the collapse of structure. So in this simulation here, in the cold dark matter case, you can see you just keep forming smaller and smaller scale structure. This is not possible in the fuzzy dark matter case, which can't form structure in phase space below h bar. And you get kind of granular density patterns. So a typical halo that you might simulate, dark matter halo, if you take a slice through its density, like we've done here, you can see you get these literal granular overdensities. Is kind of caused by the interference patterns. These are order 1 fluctuations in density. Yeah.
In those concentrations, are you estimating scale oscillations, or do you expect a difference when you scale up something?
Yeah, so there actually is a difference between scalars and vectors. That's something that people have looked at recently. Basically, the difference, the main difference for something like this is that a vector lets you put like mass into different modes that don't interfere with each other, because like the amount of mass I put in the like spin up is not going to interfere with the spin down in the same way as it would if they were in the same. So what you get is kind of the same thing you would get from having multiple scalar fields. So actually in this paper that we ran in this simulation, we looked at the kind of effect of having multiple scalar fields. And basically the effect is you just average out this density. Like, so instead of getting these order 1 density fluctuations, you now get order 1 over square root number of fields. It's the same thing with the vector, but now it's 1/square root degrees of freedom.
So like these blue parts here, this is where the scalar field actually vanishes.
Yes.
So presumably if you have a vector, you're not gonna get places where all three of the components vanish, or like it'll be.
Yeah, it'll be now whatever left, right. Yeah, but I mean, having the field go to zero and having it go to close to zero is pretty similar from like a structural formation perspective, right? And this gives you kind of a very rich phenomenology of constraints. This is the most-ish updated constraint map of fuzzy dark matter and its cosmic energy density. And there's constraints on this map kind of from all these different phenomenology that I've mentioned. So an important kind of note about all those constraints is that many of these constraints rely on the predictions of the classical field theory. And in general, we're going to require the classical approximation be kind of accurate on a very wide range of scales. So if I put up 3 constraints, just kind of picked arbitrarily from that plot I showed you earlier, and you look at the scales at which they require the classical field theory to be accurate, for something like the effect on stellar dispersion of ultra-faint dwarfs, you need this to be accurate on the de Broglie scale. For something like the constraints related to the galaxy profiles, you would need to be accurate on this kind of kiloparsec scale of the soliton. And for simulations of the entire universe, right, where we might be counting like Nokia-based satellites or something like that, we would want the classical field approximation to be accurate on like megaparsec scales. And so then understanding these simulations and this classical field approximation is going to be really essential to the model and its constraints. So the way the simulation works, right? Oh, what's up?
Sorry, I have a random question. I was just going to bring it up at the end, but since you're talking about constraints here, have you had a chance to look at this new paper by Rastafani? And I think it puts a lower bound on dark matter mass on the order of 10 feet. So it's like,
From what's the constraint?
they just argue if it's produced after inflation and it's produced via a process with like finite correlation, like then they have like a 3-page note where they claim that it's without. But it's not like earlier this week.
I mean, yeah, I haven't seen any new constraint papers this week, but that's mostly because I've been here.
Yeah,
so, but that would be interesting to look at.
Yeah, that's cool. I don't know.
But you're not sure what the actual method is, or do you know kind of what are they arguing the effect is?
It's something to do with, I think, some isocurvature formation or something.
Oh, okay.
ISO here, but it's on my to read.
Okay, no, I haven't looked at it. But yeah, I mean, I guess I'll put it on my to read list as well. So anyway, so kind of the way these simulations work, and really the way any simulation works, right, is we start out with something that we think is pretty accurate, like this quantum time coordinate equation. We think it describes the universe fairly well. And then we make some sort of series of approximations where we might take a non-relativistic approximation and get the quantum Schrodinger equation. We might take a classical field approximation to move from the quantum Schrodinger equation to a classical Schrodinger equation. And then, of course, we have to discretize it such that it's amenable to representation on a computer. And it's only after we make all these kind of like series of approximations that we get to make predictions for this model, and then use those predictions to rule out various masses. And so a lot of work has been done on kind of each step in this hierarchy for ultralight dark matter. Today, I'm going to be focusing.
Move from quantum Schrodinger equation to classical Schrodinger. What does the make of the psi and psi hat change?
So psi hat here is a quantum field operator. This is just a classical field. So
Classical field means that is kind of notion corresponding to density of particle, or
yeah, so I'll talk about this in a little bit more detail later, like specifically how, I think actually like in the next few slides, about how this approximation is done. But yeah, so here, this is the number operator for the field operator. So like this complex conjugate times this is the number operator. Here, the amplitude corresponds to the density.
okay.
or the number, or however you want to normalize it, right?
Its size, like the expectation value of psi hat.
Yeah, I'll talk about that. But yeah, if that is one way, a valid way of taking the classical field approximation, right? Where I just replace psi hat with its expectation value.
Sorry, but can you say a bit more about the motivation? You got this mass in the mind of 9 maybe.
Yeah.
Where is it coming from? Is it coming from string theory that you
Yes.
wrote this paper with? I mean, is that what it was?
So typically I'm told that these ultralight fields are like a generic prediction of string theory coming from the compactification of extra dimensions in string theory. But I'm not a string theorist. And so if you want more details about why that's motivated, I can't help you. But that's what I've been told. So does that answer the question?
Yeah, that's okay, because I'm also worried about quantum correction. You got really small mass. You're talking about here quantum, you're going to be doing all these approximations. Just wondering how robust the whole picture is.
Yeah, I mean that is the wonder that we had as well. So
I mean, if it has some shift symmetry, then the mass is technically natural. Modulo like quantum gravity correction. But
The people have written down models.
yeah, there are models to produce like axion like particles. It's like as dark matter in this I mean, like Andrew said, the misalignment mechanism. If you pick the right like scale, then you can basically get the misalignment mechanism to work at a wide range of masses.
yes.
Which degree?
Like the like f in the cosine. Oh, there's some relationship between the mass and f, which will give you the right abundance.
But this thing is this coupled to anything?
You can, but not what I'm talking about here. In any of the simulations I do, it's not.
It's completely decoupled.
Also, Eberhardt, I guess it is coming from gravity, right? So we also came out like, the gravity is classical, right? So, yeah.
So
What I'm trying to
the-
explain what it means by Eberhardt.
the gravity is non-relativistic. So, but it's, I mean, this is the solution to,
The Poisson equation.
yeah. So like,
Yeah. So in that sense, that quantum Schrodinger equation is actually a linear, right?
yes. Right.
I'm just asking just because, I know that people sometimes care about like, whether it is really correct to evaluate the Einstein equation by just taking it.
Yeah. So if you do that, then you'll get that the classical field theory is fine.
Okay.
So we don't do that.
Okay.
There's just one question, sorry.
Yeah.
I understand. So this is called document actually, right?
Yes.
Because free streaming length is extremely small, right? So I'm really this like document but doesn't have free streaming length as large as 1 meter per second. So it's called dark matter. If you classify dark matter into like full dark matter, 1 dark matter, 5 dark matter.
Yes.
It's long full dark matter, and then I think at 1 megaparsec scale, like you don't see any distinction between cold dark matter and this wavelength dark matter.
Yes.
But your work is about looking closer at the sub-megaparsec scale. And
Yes.
I wanna see-
So yeah. So I mean, in general, when I'm doing fuzzy dark matter, it's going to be cold dark matter to a very good approximation on any scale above the de Broglie scale. The kind of caveat of this is that like the your initial conditions, like the power spectrum of your initial conditions have some sort of transfer function. And so this can give you kind of larger scale effects. But yeah, basically in general, you can show that like, if I have some sort of classical field, the density is going to move around phase space exactly the same as the cold dark matter, like the corpuscular case, except on like when I start to get like structures in phase space that are about h bar.
So the distinction happens at like K versus K, for example, right?
Yep.
I see. So that's what you want to do.
Yes.
You want to see what's the distinction between these two different documents, CDM and wavelength document.
Yeah.
Okay.
Okay, so I'll get into kind of what I mean by the classical field approximation. Now. So in general, right, classical field approximation of the quantum field one is like I was saying earlier, we just take this operator here and we replace it with a number. So a classical field, right, places a number at every point in space. If I zoom in onto some point in space, there's some sort of complex number associated with that point in space, that little red dot. A quantum field operator instead acts on some sort of quantum state, which is a distribution, like some sort of probability distribution on the values of your field at some sort of position. So for instance, if it's a coherent state, right, the state that describes like really propagating photons, then we would see this kind of like tightly peaked Gaussian around the classical field value. Of course, there are other quantum states like number eigenstates, which have less well-defined phase information. And if the distribution is tightly peaked around the classical value, then we can approximate the distribution using this number, right? The number associated with the mean, a mean field theory. And so we can call the mean then of the quantum field operator the classical field and simulate that for it. So we usually motivate the classical field approximation for ultralight dark matter in two ways. The misalignment mechanism produces a quantum coherent state, right? It's just what I mean by misaligning the vacuum value of the field. I'm going to put my state to a quantum coherent state. And the occupation numbers are, of course, just going to be like absurdly large. Like a typical halo is going to have like 10 to the 100 particles in it, just because the mass of the field is so light that I'm going to need these occupation numbers. And that gives me kind of the fractional variance. So this amplitude here squared is going to give me the expectation number for the number of particles. And then the width of that little Gaussian is just set by the uncertainty principle. So if I take the occupation number to be large, that Gaussian is going to be essentially like extremely, extremely narrow. And then we can motivate our classical field approximation. Then it makes sense to approximate this distribution with one number. So what's important, though, is that both of these conditions need to be satisfied any time I want to trust the predictions of this approximation. And so it's not just enough for it to be one or the other. Both of them need to be true anytime I want to say that this approximation is making correct predictions. So this wouldn't be a problem if there wasn't any nonlinearities in the amplitude, right? So if I have a system without any nonlinearities, like this system here, where I simulate the this little quantum state, that's the blue, in this harmonic potential, and I approximate it with that little red dot, you can see that the assumption that I made at the beginning of the simulation that the distribution was well approximated by the classical field value is true an arbitrary amount of time later. I come back to this simulation, one age of the universe later, the assumption that it's well described by the classical field theory will still be true. If, however, I introduce some sort of nonlinearity, as I've done here, where I added a quartic term to the potential, you can see that on some time scale associated with that nonlinearity, the quantum state is going to be no longer well described by the single classical value. And so it might do something like we see here, where we get phase diffusion in the quantum state. And so if I come back some arbitrary amount of time later, it's not necessarily the case that the assumption that I made at the beginning of this simulation is going to be true at the end of the simulation. So kind of the fundamental question that we try to answer in this work then is, which of these cases is relevant for the simulation of ultralight dark matter? We kind of in this weakly nonlinear case where we don't have to care about any of the quantum corrections, or are we in this strongly nonlinear case where the quantum state is going to spread out on the edge of the universe and kind of ruin all of the predictions of our classical field theory? So at this point, I like to look at kind of an analogous system that kind of contains all the important components of this problem. And I'll refer to this system more throughout the talk. So basically, this is very similar to Schrodinger's cat. So we start out with an analogous system, right? So we have our cat in our box. Starts off in some state that's well described by classical mechanics. Classical mechanics pretty well describe the live cat. Now, on some time scale, some nonlinear time scale associated with whatever your like quantum mechanism is, like the decay constant of your cesium atom hooked up to your poison device or whatever, you're going to put the system into a state that's poorly described by classical mechanics, right? Like the superposition of living and dead cat, which has no classical. However, if you were to actually do this experiment, and of course, people who work in quantum mechanics do experiments where they try to create macroscopic superpositions and see how long they survive. The difficulty of this is that on some time scale, the environment will interact with your state and project it back into these kind of pointer states of the system, these like eigenvalues of the environment system interaction. So on some time scale, my environment will measure my system and project it back into states which are classical, right? Your ensemble now of living and dead cats. And so the way this system works is we start off with a system well described by classical mechanics on some time scale, some nonlinear time scale. We evolve into a state poorly described by classical mechanics, state that's purely quantum. And then on some time scale, we're projected back into a state that's well described by classical mechanics. And so this is the same thing for the fuzzy dark matter. We know that we start off in a coherent state, which is well described by the classical field theory. On some time scale, we expect the nonlinearities in our Hamiltonian to bring us to some sort of quantum state. And then on some time scale, we expect that that quantum state is going to be projected back into some sort of classical ensemble on the time scale of its interaction with the environment.
What is nonlinear?
So I mean the like nonlinearities in the Hamiltonian, they're going to spread the quantum state out. So like we go back to these simulations that I've ran, right? This one's linear. And so yeah, so your quartic terms.
Higher term in your expansion.
Yes.
But it's non-linear, like the potential is non-linear in like position variable. It's not like it's still linear as a function of the quantum state. Like you're not talking about weird non-linear quantum mechanics that's like
Yeah. Yeah. I mean, like I'm just writing down a Hamiltonian that sorry, this is the momentum space, but it has some sort of like quartic term. Okay.
Basically, that one, it doesn't have to be coming from the left side, it can be also coming from the left.
Yes. But yeah, so both of those give a separate nonlinear time. But yeah.
Are you going to be simulating self-interactions with that matter or just gravitation? Both.
Okay. So previous to our work, there have been kind of analytic estimates of this. No one was really interested in what the actual specific predictions of like the quantum state would be. And then there's been analytic estimates of this. And so what we've been trying to produce then is kind of dynamical simulations of this into the nonlinear regime. Yeah. And so, like I said, previous approaches kind of separate into different things, either some sort of order of magnitude analytic estimates or simulations of kind of small quantum states, number eigenstates. But the problem with the number eigenstate, if you remember what I showed you earlier, the quantum state of a number eigenstate actually looks quite different than that of a coherent state, which is what we expect to describe the dark matter, at least at early times. So it's not clear that these simulations can be extrapolated to anything meaningful. So this is kind of made intrinsically difficult by the scaling of the dimensionality of the quantum Hilbert space, right? So if I have some sort of system with some number of particles and some number of spatial modes, then the scaling of the dimensionality of the Hilbert space is going to go like something like the number of particles to the modes -2. So it has this exponential scaling, which kind of makes it difficult to represent anything but the smallest systems on a computer without some sort of approximation scheme. So the approximation scheme is kind of the center of the work that we've done. So our methods for approximating these are going to, I will show you the results of 3 different methods. And the kind of intention of this is to show you that all 3 of these methods are going to agree on their predictions. And so you kind of get a hierarchy of trust here in what our final results are going to be. So we're going to start off with full quantum simulations, where, again, these will work for small systems. By small systems, I mean systems with only like 100 particles and a few spatial modes, right? So this is kind of a far cry from like a galactic halo, but this is the largest thing that can be easily simulated on a computer. We've kind of developed a algorithm for simulating this, where we take our kind of total Hilbert space represented by this big square, and then we partition it using the conserved values of the Hamiltonian into a bunch of smaller sub-Hilbert spaces, and then we kind of simulate all of these in parallel, and we get kind of a large speed boost in the simulation from this algorithm. Basically, this is just kind of a complicated block diagonalization scheme, which lets us simulate systems that are quite a bit larger than it had been done previously in the literature. And we can simulate kind of a number of different systems. So these systems include both ones with a quartic term that looks like gravity and ones with kind of a quartic term that's just your phi default term. And of course, these are quite accurate because we're not making any sort of classical field approximation here. We're actually simulating a vector in a Hilbert space, but it gets infeasible to do anything beyond the small systems, right? So moving past small systems, we use this method that we developed called this field moment expansion. So for medium-sized systems then, so, you know, a few hundred spatial modes in one spatial dimension, and anything like less than 10 to the 10 particles, basically what we simulate is the classical field theory, this term here, just plus the leading term correction. So now, instead of just looking at the mean of the distribution, which is what the classical field theory knows about, we know now about both the mean and the covariances. So this is just the next leading order correction to the classical field theory.
So in both of these methods, like before you had talked about decoherence.
Yes.
And so like in my head, if you're not including decoherence, then you can just talk about a pure quantum state, and you just need to work in quantum state. But when you start talking about decoherence, you need to talk about like density matrices. So
okay.
Like here, are you just working with states?
Yeah. So nothing I've talked about so far can capture decoherence. I mean, for the full quantum simulations, in principle, you can do something to define like an environment and then do like partial traces if you want, but it's not necessarily useful from what we've done.
Okay, but when you do decoherence, then you'll have to work with density matrices.
Yeah. And so this approximation is going to give us kind of an accurate estimation of the quantum behavior for kind of at least as long as the classical field simulation is making accurate predictions. So what I have here in red is the classical field simulation for a few different simulations that we've run. The blue is the full quantum simulation, and this green line is this next leading order approximation. And so the important thing about this is you can see that it tracks the quantum evolution kind of at least as long as the classical field is making some sort of accurate prediction. The dotted vertical black line there represents when the deviation of the classical field theory is past some sort of threshold in each of these simulations. And so this allows us to estimate what we'll call the break time, so the time scale on which the classical field theory no longer makes accurate predictions, kind of using these second order moments. So the benefit of this method is that the numerical scaling is much better than the quantum simulation. So now we're no longer sensitive to the actual dimensionality of the Hilbert space. But it's still not great for like realistic three-dimensional systems because you have this 2 to the number of spatial dimensions in the scaling of your simulation. So for kind of large 3D systems, which are going to be more representative of like some sort of astrophysical situations, we're going to move to something called the truncated Wigner approximation, which is also going to let us model decoherence. So for large systems then, so kind of the systems that have the number of spatial modes you would expect in kind of simple astrophysical or cosmological simulations, we're going to have to move to the phase space of the quantum state. So we're going to look, instead of the field now, we're going to look at the Wigner function of the quantum state, which is just the while symbol of the quantum state. We can rewrite our equations of motion. So here, now you have a density matrix in terms of this while symbol. And what you'll get is that your Wigner function evolves by this Moyle bracket. It's some transform of the quantum state. I don't have it written down here, but it's, yeah, I could send it to you later. Right, and so this Moyle bracket gives us the evolution of our Wigner function, which describes our quantum state, and that's given by a Poisson bracket plus some sort of series of terms. And we can approximate the Moyle bracket as this Poisson bracket. And then we can stochastically sample the underlying Wigner function here with a bunch of fields. And then we can simulate those fields forward and use the kind of simulated forward ensemble of fields to approximate the Wigner function at some later time. And so this, from a numerical perspective, is really great because it's very parallelizable. I can take each field, and at this level in the approximation, I can simulate them forward entirely independent of all the other ones. And so I can simulate them across 500 CPUs or something and get a very large boost in the scaling of this method. So this approximation has a lot of really good properties. It has really great scaling with the problem size. So this is just the scaling of a normal fuzzy dark matter simulation. And then this number of sampling streams can be parallelized over, and so we're not punished for it, like we would in other things. And the simulation is accurate for a long time. So here I have some sort of simulation where there's a quantum state under all the little red dots, which are my approximate, my Wigner approximation. And then on the right, it's actually a little bit hard to see in this simulation, but I'm simulating the expectation value of some operator, the real part of the field, I guess. And the orange shows the approximation, the Wigner approximation, and the blue, which lies right under the orange, except for those little dots there, shows the actual quantum value. So this is accurate for a long time. Usually, we would expect that the Wigner approximation would be accurate until something called the Ehrenfest time, which scales as the root of the number of particles. So for the kind of systems that we're interested in, this is a very, very long time. We can also use this to model decoherence. This kind of specific test that we're going to run is we're going to define a system which includes now the environment and the dark matter component. We're going to model some sort of interaction between the two of them, like gravity. And we're going to use a Hamiltonian and, that interaction Hamiltonian and a joint Wigner function, which is now just the product between our environment and our field Wigner function to describe the joint evolution of the system. We're going to just add one test particle to the system representing some sort of baryonic matter or something like that. And kind of the important thing about this is that for baryonic luminous matter, right, we know that it takes well-defined phase space trajectories. So we know that our decoherence rate is going to have to be at least as fast as our tracer particles go into some sort of macroscopic superposition. Because of course, if you take luminous matter and you give it some sort of trajectory through phase space, it doesn't enter into the superposition of itself here and here, right? It takes some sort of well-defined track. Okay, so now we have these three different methods using three different equations of motion, three different representation of the quantum state, but they're all going to give us kind of the same results. Go over those results right now. So first, we're going to look at this nonlinear time and just kind of estimate the time scale on which quantum corrections grow. Of course, if this is much longer than the age of the universe, then we don't need to do any of the follow-up analysis, right? I'm going to parameterize these quantum corrections using just some value Q here for quantum, where I just compare the size of the second order moment, right? So this leading order correction to the classical field equations to the amplitude of the field, which gives us the total number of particles. And this goes from 0 to 1. This is not a unique definition of quantumness. It's not even the only definition we looked at. But kind of the important thing about this is that it's a fairly reliable indicator when there are differences between quantum and classical evolution. So here I've simulated some typical halo, sort of dark matter halo. You can see it has the granular structure that I showed you earlier. And you can see that the case of the quantum evolution when the Q is quite small is very similar to the classical field, but if Q is large, then it's quite different.
What's the difference between cold dark matter and wave dark matter? For the coherent model.
What's the difference between cold dark matter and wave dark matter?
How does the model get different for these two different cases? Or there's no distinction.
I'm not modeling cold dark matter.
Well, you said you were going to compare these two different cases.
Oh, sorry. No, I was going to compare the different cases of classical and quantum wave dark matter. I'm not comparing, like, so, I mean, there's obviously a huge body of literature comparing fuzzy dark matter to cold dark matter, right? That's arguably all the literature of fuzzy dark matter. But I'm looking at specifically the classical field approximation used to make these comparisons. So I'm not modeling cold dark matter at all. Yeah, sorry. Hopefully that clarifies.
What would be the difference?
What?
Difference in the coherence model for cold dark matter and wave dark matter.
Sorry, why would there be a difference?
I'm just wondering, like, is there any difference? If not, then you can say no. I'm just wondering, is there any difference in the coherence model for these two models? And we feel like dark matter.
Yeah, so I mean the Hamiltonian for no, I think it's just no, there's not, because I could just take the mass of my scalar field dark matter to be really high and I would get the dark matter. Right. So I guess if your cold dark matter is not spin 0, then it's different than what we've modeled here. But if it is, then there's not. And if it has some sort of interaction term that's not gravity, then it's different too. But we haven't modeled that in this decoherence.
Why is the mass coming in?
So just because if I take the mass of my ultralight field to be really, really heavy, then kind of all of the like wave phenomena that people are interested in from a fuzzy dark matter perspective go away, and then it's just cold dark matter.
But if it's light and you make it, you remove the wave-like features of it and make it in particles.
Yeah.
You just have a lot of them. So
Yes.
what's the difference then?
There's no difference. Yeah. You're not going to get these like wave-like phenomena on astrophysical scales. But there's no like, yeah, there's no other difference other than that you're like not going to ever resolve the de Broglie scale with whatever probe you're using.
So you're just asking now, how long is the wave-like feature persisting? Because if you go through decoherence, then presumably you're making particles out of your quantum state.
Yeah, if I go through decoherence, I would think I would probably be making classical fields out of my quantum state, but
Fine. The classical fields or particles And so you're gonna lose some of this, like a fine scale structure, right, between these different pictures
Yeah,
that you're simulating.
yes,
And so the goal here is then to find out what that time scale is.
yes, yes. So we're looking both at the time scale on which these classical field structures disappear. And then we're going to look at kind of the effect of the large quantum corrections, which, as you can see from here, it's just that most of the like fine scale granular structure disappears. And then we're going to look on the time scale that you're projected back from here. Good. Okay, cool. So the first analysis that we're going to do is look at how long it takes for these quantum corrections to grow to some size. So this first time scale that I just mentioned just now, as a function of like the total number of particles, which you should think as kind of parameterizing the initial size of the distribution or of the spread in the quantum system. Oh, sorry. So for the full quantum simulations, we see this kind of logarithmic scaling with the number of particles. For our one spatial dimension simulations, we're going to simulate kind of this classical astrophysics test problem where we look at the gravitational collapse of an initial spatial overdensity in one spatial dimension. In the fuzzy dark matter case, it looks like this, which is basically the same as it looks for the corpuscular dark matter case, but you can of course see the interference patterns that are typical of fuzzy dark matter and the density there on the right. If you look at the time scale it takes for the quantum corrections to grow in that system, here you see the same logarithmic scaling, the same kind of time, or the same effect as, or the same scaling that you get in the full quantum simulations, where you get this kind of logarithmic enhancement in the time it takes for the corrections to grow to a certain size with the particle number. This is kind of a well-known result predicted for systems which exhibit classical chaos. And it's kind of straightforward to understand why this should be the case in the truncated Wigner context. So, what's up?
So those kind of time scales, I assume depends on the initial function. Like, you know, so you say like initially you are assuming this elements of theorem, but
Yes.
could you specify a bit more what you actually assume? Because think about like here is like so if you produce like a scalar field from this element content, then it's homogeneous and then the theorem always the dominant. But if you produce vector bosons during inversion, for instance, then like if I remember correctly, the spectrum is more like produced data in have some peak at some finite momentum.
So yeah, so we're assuming that it's a coherent state initially centered on the classical field values.
Okay.
Which
so
is
the moment of expression is something like this.
So if the initial quantum state is something different, then yeah, you can get the corrections to grow at a different time scale. So for instance, if the initial quantum state's a number eigenstate, then the classical field theory is just trash from the beginning. But yeah, I mean, this is kind of the assuming that it's the coherent state is kind of the conservative assumption for looking at the quantum corrections, right? Because if I just assume that the quantum corrections are large at the initial conditions, then they're large at the initial
I think
conditions.
it's really with the inflationary vector production. I think it's still a coherent state. It has some spectral dependence, but it's still.
Yeah. That's what I mean.
Okay. Thank you. Right. So these two left panels are the panels I just showed you earlier for the classical field simulation of the collapse of initial overdensity in 1D. But now I'm showing you on the right a zoom in on one position of the classical field value. That's that little red dot in the complex phase space. And the Wigner approximation of that, which are the little tiny black dots. So you can see that at the initial conditions, the distribution is well approximated by the red dot. Right? But as the simulation progresses, the underlying quantum distribution undergoes phase diffusion. And at some later time, it's no longer well described by the single red dot. And the result of this is that the evolution of the quantum system, which is this blue line here, is missing this kind of de Broglie scale interference structure, right, which we alluded to. So the second analysis that we're going to do is look at the time scale in which Q grows, right? So if I plot Q over some time, it looks like this. This is pretty typical. What you're going to see is this kind of staged growth where initially you start off with an initial quadratic growth, which is just given by this kind of commutation term in the Hamiltonian, which seeds you from 0. During the nonlinear growth of the system, so during this kind of exponential growth phase, you get this exponential growth in the quantum corrections, which accounts for our logarithmic scaling. And then after the collapse, when you're kind of in this like virialized system, you get some sort of power loss or some sort of very slow growth in the size of the quantum corrections. So any power law growth is going to be way too slow to create quantum corrections on the time scale of the universe, right? Because our particles numbers are so astronomically high that if your quantum corrections are growing this slowly, then you never ever need to care. But exponential growth may be a problem. And so that's kind of what we're going to focus on going forward. So what we're going to look at now is how this behavior generalizes the three-dimensional system. So like I said earlier, we can simulate three-dimensional systems using the truncated Wigner approximation. We're going to use 3 different test problems. So kind of the collapse of a random field. So it's kind of hard to see here, but there are little random Gaussian overdensities there. I let it collapse into some sort of object there. And then I might want to also look at just the behavior of that collapsed object. So some sort of stable object that is post-collapsed, and then the merger of 2 collapsed objects. So this kind of represents the typical things you would expect some sort of galactic halo to do. So like a halo can of course collapse out of your kind of initial random perturbations. It can sit there virialized, or it can merge with some sort of other virialized halo. So these 3 test problems then are kind of designed to show us how would the quantum corrections behave in the typical activities that a halo can get up to. So basically the results corroborate your 1D expectations. So during the collapsing phase of the halo's life, you see the kind of exponential growth in the quantum corrections, just like in the collapsing phase of the one-dimensional overdensity. When it's just sitting there being a virialized halo, the quantum corrections only grow by a power law, by this quadratic growth, which again was the same in the one-dimensional collapse. Right after it collapsed, the corrections grow quite slowly. And then when it's merging, merging is very similar to kind of nonlinear growth, right? Then you also see this kind of exponential growth in the quantum corrections, right? And this kind of also corroborates our intuition about the way quantum corrections depend on the chaotic behavior, like the classically chaotic behavior of these systems, right? In the kind of collapsing emergent phase, this is much more chaotic than it's just sitting there virialized. So yeah, just like the 1D results, we're seeing that you get power law at very, very early times and post-collapse, but then during any sort of nonlinear growth phase, you get kind of exponential growth in the quantum corrections. So we can then say that the time scale for quantum corrections is going to be logarithmic with the number of particles, and then kind of be some order 1 number here times your dynamical time of the system. So we'll take a look at the quantum state now. Again, I've talked about this already a few times, but the predictions of having large quantum corrections is essentially just to remove the density fluctuations from the interference. If we look at the truncated Wigner approximation again, we can kind of see why this is occurring. So as the state evolves, the nonlinearity causes this phase diffusion here. So the phase of the quantum state is no longer well defined. Of course, when the streams cross each other in the classical phase space, for the classical field approximation, this causes these interference patterns, which goes as the gradient of the phase. But we don't have a well-defined gradient for the quantum system, so we don't get the kind of oscillating de Broglie scale structure that we see in the classical field case. So you can see here that if I run different simulations with different sizes of the quantum corrections, that the effect is just to make these order one density fluctuations smaller and smaller. So from a constraint perspective, this is going to matter most for kind of constraints that are most sensitive to these like full nonlinear structures, right? So for instance, the heating of ultra-faint dwarf stellar dispersions, or the constraints coming from gravitational lensing, right? Where in the first one, these kind of density fluctuations kick stars around, and this causes stellar dwarfs to expand beyond what is currently measured. In the second constraint here, essentially these granules in the density prevent the light from some sort of simulated jet from focusing in a way that's consistent with the observations. And so essentially the implication of these large quantum corrections would be just that you get a less granular density and you would reduce whatever constraints come from the granular density. But now, of course, we're interested in the timescale on which the quantum state is going to be projected back into some sort of classical state. So again, we did this with the coherence test the decoherence test that I described earlier. So we couple our dark matter state now to a test particle. So in this simulation, I'm showing you here the distribution of the test particle. So the red is the classical value of the test particle. And then here, and otherwise it's the same simulation that I showed you earlier. You can see as the simulation progresses, the test particle goes into some sort of macroscopic superposition on phase space. And then evolves into kind of this distribution now on phase space. And if we look at the timescale that this occurs, we see that it actually occurs at the same time as the quantum corrections are introduced. So this is the test particle uncertainty. Here are the quantum corrections in the classical field. And you can see that they're essentially evolving in the same way. And of course, this is because unlike Schrodinger's cat, both the quantum corrections and the decoherence are caused by the same thing, right? The nonlinear effects of gravity. So the spread in the particle's wave function is caused by its gravitational coupling to the classical field, it's coupling to the quantum field, but of course the spread in the quantum field wave function is also caused by its gravitational coupling to itself. And so this kind of makes it kind of unlikely that we could evolve into a state with large quantum corrections without also putting test particles into macroscopic superpositions. Of course, we don't observe it, right? We know that the baryonic particles take well-defined tracks through phase space. And so it's difficult to imagine that we could evolve our kind of underlying quantum distribution into some sort of macroscopic superposition without also putting classical particles into these same superpositions, which we don't observe. So we can say then that the decoherence timescale should be at least as fast as the nonlinear timescale, or at least of order the same. And so now we've produced simulated results into kind of nonlinear regimes for these three things, which previously only had some sort of analytic estimates associated with them. So in conclusion, then, we expect our quantum corrections to be growing exponentially during systems which are experiencing nonlinear growth, and then slowly in systems otherwise. The kind of effect of these quantum corrections is to remove granular interference structures from the density. But we would also expect that decoherence should be happening at least as fast as quantum corrections grow. Kind of the takeaway from this is that the decoherence is probably going to save your classical field approximation. And so I would say this is fairly strong support for the predictions of the classical field theory. The one caveat to this, which I'll mention, is that we didn't look at the actual quantum states which describe the Poynter states. Of course, it's possible that the Poynter states are not coherent states, right? And so if that's the case, then you would have to do more work to determine what the kind of end predictions of those Poynter states would be. But if you assume that they are coherent states, then your classical field theory is likely quite accurate. So yeah, I'll take any questions. I think we're almost out of time.
Yeah, do we have any more questions for Andrew? I'll ask for starters. If you forget about the decoherence, just look at the nonlinearity time. Are there any physical systems where the nonlinearity time is like some reasonable time scale, like less than the age of the universe?
Yeah, so I mean, because it's going as a dynamical time, right, which is just given by the fact that these like quantum corrections are going because of the like classically chaotic behavior of the system, right? I mean, I can get a small dynamical time for like any sort of large like system. So some sort of really large galaxy is going to have a short dynamical, right?
I mean, like for like the Milky Way, the dynamical time is basically like the rotation theory.
Yeah, like a typical orbit is the dynamical time of the system. So yeah, you're kind of also protected by that because all the constraints that I talked about that are going to be most sensitive to these quantum corrections are like, you know, ultra faint dwarfs or something like that, which is a dynamical time change. So I think if you look at the like the time scale, you would expect the quantum corrections to become order 1 for like an ultra faint dwarf, and it is like 35 gigayears or something. But for like a larger system, it would be less.
Well, because like on some of your 3D simulations, when you're plotting Q, the like vertical axis is like 10 to the
Yeah.
minus 90 or
Right.
whatever. So I guess like it grows on the dynamical time scale, but if you started out very small, then you need many dynamic.
Yeah, then you need many e-foldings to get it to be order 1. Yes.
What's that the starting Q that you?
So so the starting Q in principle should be 0 because if you saw the way I defined it earlier for a decoherent state, or sorry, for a coherent state, that second order operator is 0. And the reason the Q is so small in those plots compared to some of the other plots I showed you is because like, so if Q is less than 1, you can show that if I kind of change the number of particles in my simulation, which parameterize the initial size of the quantum corrections or the initial like spread of the wave function compared to the amplitude, then the evolution is the same. So I can rescale my results by like the physical number of particles in the system, which is like 10 to the 100, but I can only actually simulate like 10 to the 14. So that's why those cubes are so small compared to them. Does that make sense?
Oh, okay. So I shouldn't. That was more of a numerical reason.
Yeah,
That
that's
you said it.
yes.
But okay, like the actual cube might have started much larger, so you don't need that many dynamics.
No, sorry, it's the other way around. The actual Q would start much smaller. Right. So the one I showed you that was like 10 to negative 97, that's the physical value of Q, right? My numerical value is much larger than that because I can't represent a number that's 10 to negative 97 on a computer, right?
Okay, gotcha.
And then I rescale it by the physical number of particles in the system after the fact.
So I probably need like hundreds of dynamical timescales, but there might be galaxies for which that.
Yeah, so like again, like your kind of large spheroidal galaxies, that dynamical timescale is going to be quite short, and so you can get quantum corrections, not considering decoherence on the timescale of the universe quite easily. But for like ultra faint dwarfs, like there's no way.
Okay. Yeah, here again.